Great. In Chapter 2, Section 7, we're going to be looking at inverse functions. Inverse functions undo each other. When we solve equations, we use inverse operations to undo or solve. So inverse, like addition is the inverse of subtraction. Subtraction is the inverse or undoing of addition. Multiplication and division are inverses of one another. So for this algebraic example here, if we were going to solve this equation to get rid of the addition of 3, the inverse is to subtract a 3, which results in 2x equals 4. Now x is being multiplied by 2, so to undo multiplication by 2, we divide by 2 on both sides of the equation, and the result is x equals 2. So we're going to be looking at inverse functions where this was inverse operations. All right, so what about the graphs of inverse functions? Well, the graphs of inverse functions are a reflection of each other about the line y equals x. So right here I have 3 different problem situations, graphs that illustrate what inverse functions are. So first of all, let's make sure we can identify that this is one of the common functions we've seen in our previous lesson, and this dashed line right here is y equals x. So right here is y equals x. And in this third example, it's kind of hard to see, but this is actually y equals x right here. Okay, so when we look at, in this first example right here of these graphs, when we look at the equation y equals 2x plus 3, that's a linear function. It graphs a line. When graphed, it looks like this. Well, notice that if you were to reflect across y equals x, that the reflection would produce this graph down here. Another way to think of it is if you were to fold along this highlighted yellow graph right here, this equation, that these two would lay on top of each other and coincide. So these two linear functions are inverses of each other. Okay? And another thing to think about is that both these linear functions pass the vertical line test individually, so both of these are functions. All right, look at f and g. Well, here's f. It kind of looks like one of our well, it probably is one of our parent functions, our common functions, and this is a cube graph. If you were to reflect across y equals x, okay, then what you're going to end up with is this cubed root graph. That was another one of our 7 common functions in a previous lesson. So when folding across again, the highlighted yellow y equals x, okay, both of these graphs would coincide and lay on top of each other. So one of our objectives is to be able to identify whether or not a set of 2 graphed functions, okay, are inverses of each other. Okay, right here, we've got, this is an exponential function, which we'll study in more detail in a later lesson, but when reflected across y equals x, okay, we can see that this right here would be a reflection of this exponential graph right here. And this is actually called a log graph, and we'll study that again in more detail later. So hopefully visually you can see what inverse functions would look like. They have symmetry along y equals x. We've seen symmetry before. What we were looking at symmetry with regard to the y-axis, that was an even function. And we also saw symmetry with the origin, which meant we had a double reflection, so that the graph coincides or is a mirror image of itself across the origin, which is accomplished through that double reflection. All right, well, these are all examples of inverse functions. So let's dig in a little bit further to inverse functions and some characteristics. So the domain and range, there's something interesting that happens with inverse functions. So the inverse of a function is the set of ordered pairs obtained by interchanging or switching the x and y values of each pair in the original function. So here's an example. If f of x is an equation and g of x is an equation, and they're both functions and they're inverses, okay, let's say that f of x contains these ordered pairs. So -3, -7, -2, -4, and 0, 2. Let's say that those 3 points are on f of x. We'll say that those are the x and y coordinates on f of x. Well, what are some coordinates that are on the inverse of f of x, or what are some coordinates that are on g of x? Well, g of x must contain the ordered pair -7, -3. And kind of look right above it, you can see that all I've done is interchanged or switched, okay, the x and the y coordinate. So here, if I switch the x and the y coordinate, I get -4, -2. Here, switching 0 and 2 results in 2, 0. So these 3 points right here would be points on the inverse function. So that would look like y switched with x right here. So kind of a quick example looking back up here at one of these just to kind of verify what's happening here with our graphical representations. So let's just look at, say, maybe on this red graph, let's look at the ordered pair 0, 3. Well, if 0, 3 is on a function, then the ordered pair 3, 0, when I switch those, must be on the inverse. And if you look at what we said was the inverse, this point right here is 3, 0. Okay, maybe one more. Let's look at another point that's on y equals 2x plus 3. Let's look at the ordered pair 1, maybe 5. So if 1, 5 is on f of x, then 5, 1 must be on g of x, or the inverse. And it is. 5, 1 is going to be a point on its inverse function. So that's all it's saying right here. With the individual ordered pairs that belong to functions, we just switch the x and y coordinates to obtain a new point that's on the inverse function. All right, well, sometimes this can be an issue. Let's look at this even function, another one of our common functions we saw in a previous lesson. Let's look at the f of x equals the absolute value of x. So from memory, hopefully you might remember that's a V-shaped graph. The parent function looks something like this. It's an even function, meaning it has symmetry with regard to the y-axis. Okay, so let's look at the absolute value function. So graphically, if I were to take and kind of on a different grid, maybe not the same grid, what if I want to kind of see if I can sketch out what its inverse would look like? Well, I might want to consider that I have to think about y equals x. That's the line of symmetry. Actually, this part of the absolute value graph is already on y equals x. So if I were to reflect across y equals x, it would actually just be itself. The problem here is when I take this part of the absolute value function and I reflect it across y equals x, it's going to come down here. Why is this an issue when we switch x and y? Because sometimes then when we do that, this inverse graph is not a function. Graphically, remember that a function has to pass the vertical line test. And if I were to put a vertical pencil here, you can see that I have two y's for the same x value. So unfortunately, the absolute value graph does not have an inverse. It has an inverse graph, but this graph is not a function. So what does that look like with some of the points on the graph? Like we can see it visually, okay, that the function, the absolute value, passes the vertical line test, but its inverse graph does not. All right, well, let's look at some individual points and see what causes this issue. So some points that are included in the domain of the absolute value graph are like -2, 2. So maybe that's right here. Another point is -1, 1, which is maybe right here. We also have 0, 0. Another ordered pair on the absolute value graph is 1, 1, and then maybe 2, 2. Okay, well, that's all fine and good. Now, if we have an inverse, then we switch -2, 2, and we get 2, -2. Switch this ordered pair. +1 comes first, -1 is second. Switching this results in the same. And then likewise with these last couple of ordered pairs, when you switch them, you get the same. Okay, so if we do that, if we switch the x and y, now let's look at this new set of ordered pairs. Does this relation right here, which is a set of ordered pairs, define a function? Well, we look for repeated x's. I see a 2 here, but I also see a 2 here. So I have the same x that gives me two different y's. So no, this ordered pair would not suggest that we have a function, or this relation would suggest that we don't have a function. So and actually these are the ordered pairs that belong on here. So visually we can see that we don't have an inverse graph that is a function, and then we can kind of further prove it by looking at some individual points and how we have repeated x's. All right, so a little bit more about that. What if we wanted to, what's all going down here is, let me use this example right here. This whole information right here is going to help us determine, without looking at ordered pairs, whether a graph, if we can see it, okay, would have an inverse that is also a function. So like back up here, when you look at y equals 2x plus 3, that passes the vertical line test. Well, its inverse graph, which is in green, it also passes the vertical line test. So the inverse of this function is also a function. Same thing here with f of x. Notice that f of x passes the vertical line test. Its inverse also passes the vertical line test. And then the same thing happens here. This exponential in red passes the vertical line test. Its inverse graph also passes the vertical line test, so it is also a function. Now, I know that's a lot going on there. Okay, so what this is saying down here to us is that if your original function fails not the vertical line test, but a horizontal line test, that means that its inverse will not be a function. Okay, so all that to say this. Look back up here at the absolute value of x. We know that the absolute value of x is a function. It passes the vertical line test. But if you try to do a horizontal line test on it, notice that it would fail that same kind of test. That you would have two y's here, okay, for two different x's. So if I fail the horizontal line test, that means that when I reflect across y equals x, if I fail the horizontal line test here, I'm going to fail the vertical line test right here with the inverse graph. So sometimes if we just look at a graph and it passes the horizontal line test, we know that its inverse will also be a function by passing the vertical line test. And that's kind of all that's being said here. So let's see if we can kind of make sense of these words. So it says the inverse of a function may not always be a function, as in this case right here. That inverse was not a function. The original function must be a one-to-one function to guarantee that its inverse will also be a function. Then it goes on to say a one-to-one function is a function with no repeated y values. Well, here I've got repeated y values all over the place. We can determine repeated y values, and we can determine if a function is one-to-one by using a horizontal line test. So the horizontal line test for inverse functions. So a function f has an inverse that is also a function, and if we do have one, we could use this notation, f inverse. Okay, if there is no horizontal line that intersects the graph of the function f at more than one point. Okay, simply put, let's look at this graph right here. Okay, let's look at this original function we have. Does it pass the horizontal line test? Yes, it does. Okay, so that means that if I were to reflect across y equals x, I'm going to draw in y equals x and try and sketch it out here. It means that its reflection right here, let's see if I can do this. Its reflection right here would pass the vertical line test. So if the original function passes the horizontal line test, which it does, then its reflection will pass the vertical line test and also be a function. All right, let's look at this graph right here. Looking at this graph of this quadratic right here, I can quickly see that I have repeated y values. So that means if I were to reflect this across y equals x, it's going to be a parabola or a quadratic that lays on its side somehow. I'm sure that's not correct, but as far as the drawing. But if you put this parabola on its side, notice how you would fail the vertical line test. So this inverse graph would not be a function. So what we want to take away from here is that a one-to-one function passes the horizontal line test. A one-to-one function means that the inverse will also be a function. Okay, so let's take a look at some graphs here. Here we have some examples, A through H. The question is, do these functions, they all pass the vertical line test, do these functions have an inverse that is also a function? So when we read that language, and it wants us to know if, without graphing the inverse is a function, all we have to do is look at a vertical line test. So for example A, I have repeated y values, a lot of them. So I fail the horizontal line test. This is not a one-to-one, it's a function, but it's not a more qualifying one-to-one function, which means that when you draw its inverse across y equals x, something like this, that the inverse would fail the vertical line test and the inverse would not be a function. All right, what about this graph, B? So we're gonna put no here. Does graph B pass the horizontal line test? Yes. that means that when I draw its reflection, however we want to do that, across y equals x, that graph would pass the vertical line test. All right, in example C, we can see we have no repeated y values, so we're passing the horizontal line test. So the answer here would be yes as well. Pass the horizontal line test? The answer is yes. Okay, and just take a look at those last four and see if you think each of those would pass the horizontal line test. I'll put the answer here, yes. These graphs just continue onward like this in both directions, but they have no repeated y values. Okay, in graph F, I have a bunch of repeated y values. So if I drew the reflection on its side, okay, it's going to fail the vertical line test. So this is a no. We've seen this one. This function does not have an inverse that is also a function. And then right here, we can see that we have repeated y values. If you put a horizontal pencil, something horizontal here, a toothpick or a pencil or something, you got a lot of repeated y values. So the answer is no here. All right, moving on with some more topics with inverse functions. Let's look at the algebraic definition of an inverse function. So let's say we have two equations. Let's say we have f and g and they're both two functions. If if f and g are inverse functions, then their compositions, we saw that in section 2.6, their compositions will always simplify to x. Right here in this black line box, what it means is if I were to put g inside of f, remember this is not multiplication, this is a substitution operation. So this is composition. If I were to put g inside of f and then do a lot of cleanup, if I get x, that's a good start. I'm halfway there. But I also have to then go the other way and put the f equation inside g, do the cleanup. If I also get an x out, then that means that f and g are inverse functions. So if I can't look at a graph to determine if I have inverse functions, but I have equations, if I do these two compositions and clean them both up, and get the same answer of x, not negative x or 2x, just x, then I know that f and g are inverses. All right, and then again, a reminder about the inverse function notation. If we do have inverse functions, sometimes instead of calling them f and g, we might say, okay, well, f is the function and f inverse, okay, would be the notation that's the name of or the label for the inverse. All right, well, that's a lot so far. So if you're ready, we'll go on. And if not, just kind of pause the video, take a brain break, and go back and look at some of the content that we've already discussed. All right, for number 1 and 2, it says verify that the given functions are inverse functions. So they're telling me that f and g, when graphed, would have symmetry across y equals x. So that means when I do the two compositions, f of g and g of f, that when I do all that math, I should get an answer of y equals x, or just x, the line of symmetry. All right, so let's go back and revisit the composition. So I'm going to put g and f. So I look for g, and then I look at f. So I look at f, and I go, oh, okay, f's the outside function. So wherever the x is, I'm going to put a big parenthesis. And then right here is where I'm going to put the g inside that x's spot. So I'm going to put the fraction x plus 7 over 4. All right, I'm going to go ahead and bring this notation down. It's good to have that label all the way down through. So left-hand side of the equation is the name of what I'm doing here. All right, order of operations. We have to demonstrate the correct order. All right, I have to do the multiplication first. Well, I can make 4 a fraction by putting 4 over 1. So I'm multiplying this fraction 4 over 1 times x plus 7 over 4. Well, I'm going to divide out these 4s into 1s. And so I'm left to multiply the numerators together, and I get x plus 7. When I multiply the denominators together, I also get 1, but there's no sense in putting this over 1. Don't forget to bring down the minus 7. Okay, and then I'm going to bring this name down again. Continuing the cleanup here, I can see that the 7s will cancel, and I'm left with x. So the composition f of g of x does give us x, but we can't say that these are inverse functions until we do the other composition, g of f of x, and also get x. All right, so now F is the inside and G is the outside. So my eyes land on G. I built G, but wherever I see the X, I put a parenthesis. So it still has a plus. So this was X plus 7 over 4. But the F equation now goes in for that X. So now I put 4X minus 7 here. I'm ready to come down, so I bring the label, the notation. Now let's focus our attention over here. Well, these parentheses don't matter because I don't have a power or anything to distribute, so really I can just remove those parentheses. Okay, in the numerator, I can kind of see that I can cancel these 7s. So let me not crowd this problem. Let's kind of take a couple of lines here. Let's bring down 4X over 4. Well, now I can divide out the 4s from each other because now I have just factors. Now I can. So my answer is X. So both these compositions resulted in a cleanup of X as an answer for each of them. So we just verified that that function, when graphed, and that function have symmetry across y equals X. Let's look at 2. Another example, verify that these functions are also inverse functions. So f of g of x and g of f of x, and our new functions are right here. So g goes in f. So here's g and here's f. So I'm going to write down f. It's the cube root, and I've got an x here. So there goes a parenthesis, minus 4. Now in the parenthesis for that x, I'm going to insert x cubed plus 4. Let's bring down the label. Okay, some students want to go right away to cube rooting x cubed, but we can't do that yet because we can't cube root just individual terms underneath here. So do we need these parentheses right here? They're not necessary because I don't have a power and I don't have a coefficient to distribute in. So those parentheses they can be removed. Once I remove them, I see that I can cancel these 4s. Let's not crowd our work. Let's bring this line down again. We still have now the cube root of x cubed. All right. Well, cube rooting a cube power undoes. Those are inverse operations. Okay, so now we're left with just x. So we're going to bring x out. Do I need absolute value? That's kind of another thing we have to think about. No, I don't need absolute value because that's an odd root that I brought in. So far so good. I'm halfway there. Let's verify that this composition also results in x. So f goes in g. So I put my eyes on g. Here's x. I'm going to cube it. And then I've got the rest of the g equation. So now right here where x is, I'm going to insert the whole f equation, the cube root of x minus 4. All right, let's kind of take a look at what we have here. I have to cube this cube root. I have to do the power before I do the addition. So cubing a cube root, those are inverse operations. So out comes everything that's underneath the cube root, called the radicand. So I bring out x minus 4, and don't forget the plus 4. All right, and then right here we can cancel the 4s, and so we're left with x. So here we've just verified that the given functions are inverse functions by doing 2 compositions, and when we do the correct order of operations, okay, both those compositions result in x, which happens to be the line of symmetry of y equals x. Okay. In the next video, what we're going to do is we're going to learn how to find an inverse of a function, meaning we're going to be given one of the 2 equations that are inverses, and then we're going to follow these set of steps to get the inverse equation. Okay, and we'll do that in the next video.